Dear students, today we will learn about Young's double slit experiment. In the previous video, I have told you that interference can be broadly divided into two types. One is by division of wavefront and another is by division of amplitude. This Young's double slit experiment falls under the category of division of wavefront, right? The next thing is that for interference, we need two coherent sources of light. By coherent sources, we mean those two light sources which have almost same frequency. Now, the question is, why do we need these coherent sources? Why do we need sources of same frequency? And the answer is here. Suppose you have two waves, one is traveling quite fast in a given interval of time, and another is covering lesser number of circles in this interval of time. So, what will happen? That in a medium, since this wave is traveling fast, it will advance and this will remain behind. So there are lesser chances that such waves can meet again and again in this medium. There are lesser chances that they can superimpose again and again to produce interference. Therefore, the thing is that interference will happen at some point of time when they meet in the medium, but that interference will not be a sustained interference. If we want that interference to happen continuously, to happen on a sustained basis, the condition is that the two waves should have a same frequency. That is, they should be covering same number of cycles in a given interval of time so that they meet again and again. They hit their crusts and troughs again and again to give those bright and dark spots. Now, if that condition is not met, we will have interference, but that will not be a sustained interference. If you have understood this, now let us move to Young's double slit experiment. Again, you have a source of light that is illuminating two slits, right? The wavefronts are of this shape and they keep advancing. At certain points, you have constructive interference. At certain points, you have destructive interference, and corresponding to which we obtain bright and dark spots on the screen. Bright and dark spots on the screen. Now, let's try to do this mathematically, analytically, right? If one of the waves coming from slit S1 and another wave coming from slit S2 are represented by these two wave equations, y1 is equal to a sine omega t and y2 is equal to b sine omega t plus some phase difference phi. A and b are the amplitudes of the two waves that are emerging from S1 and S2. They have slightly different amplitudes and they have some phase difference phi. That is how we choose the conditions initially, right? Now, the principle of superposition, as is known to all of you, is that y is equal to y1 plus y2. The total displacement, the total disturbance at one point in a medium due to two waves is equal to the sum of the two. Now, y is equal to a sine omega t plus, here you can write it as sine a cos b plus cos a sine b plus b times sine a cos b plus b times cos a sine b. Now we can also choose to take out some common factors. For example, sine omega t is common here. Inside what remains is a plus b cos phi. Here you can write cos omega t. Inside what remains is b sine phi. Now we can put this equal to r cos theta in analogy with the thing that you have a cos factor inside. So you put it equal to r cos theta and you put this equal to r sine theta. What are you left with? Y is equal to sine omega t r times cos theta plus r times cos omega t sine theta. So in total you have r times sine omega t plus theta. This is the resultant wave, expression of the resultant wave, and r is the amplitude of the resultant wave. Again, we have used the formula that sine a cos b plus cos a sine b is sine a plus b. Now what can we choose to do? What more can we choose to do is that let us square and add these two factors. What do we get? R square cos square theta plus r square sine square theta is equal to a square this plus b square cos square phi plus 2ab cos phi plus b square sine square phi, right? So this will also be 1, so we will be left with r square only. This will be a square plus b square plus 2ab cos phi. So because we know that the intensity is given by the square of amplitude, we can also choose to write it as the resultant intensity is the sum of intensity of one slit, intensity from another slit twice. I can put an under root I1, I2 cos of phi. Now depending on the values of this phi, we can say whether the intensity is minimum or maximum. We know that the values of cos range from cos of an angle range from plus minus 1. So cos is plus 1 when the angle is even multiple of pi, and it is minus 1 when it is an odd multiple of pi, right? So we can say that cos phi ranges from plus 1 to minus 1. This is the maximum value and this is the minus value, this minimum value. Now let us turn to next page. So if this phi is 2n pi, the value will be maximum, and if this phi is 2n minus 1 pi, the value will be minimum. And what will be that? That r will be equal to r square is a square plus b square in case of maximum, because it will be cos 2n pi, that will be plus 1, it will be only 2ab. So you are left with r square is equal to a plus b whole square. So r is equal to a plus b. In other words, r max is a plus b. Similarly, r min is a minus b, corresponding to which I max is a plus b whole square, and I minimum is a minus b whole square. Now if you choose to make the two amplitudes equal, what is the maximum value of intensity? A plus a, 2a, right? 2a whole square, and here it is 0. A minus b, that is a minus a, 0. This is in case you choose to make two amplitudes equal, right? Now in addition to that, what more do you need to do is to find the fringe width. Find the fringe width, because you know that alternate bright and dark spots are being formed. We need to find what is the width of the fringe, and in the subsequent derivation you will find that between two bright fringes there is a dark fringe, or alternatively between two bright fringes there is a dark fringe, and we are going to show that all the fringes are of same width. Now let us begin the expression for that, the derivation of that. So here is the screen. These are the two slits. Suppose this is the central position C. You have a light wave hitting here. You have another light wave from this slit hitting here, right? So suppose the two slits are at a distance d from each other, and the screen is at a distance capital D from the two slits. Suppose the central position is at a distance x from the spot where we are interested in, where the two waves have met. We want to see whether a constructive or a destructive interference has taken place. That will be determined by the path difference. How do you understand that path difference? You can see that the length of this path, this ray of light, is shorter than this. By how much amount? If we draw a perpendicular, then it's a kind of isosceles triangle, and this ray of light has traveled an extra path this much, right? We need to find it out. Now let us do that. So let's name this point as P, right? So let us do it here. Let us do it this way, right? This distance is D. So you have to find the path difference. You're interested in the path difference S2P minus S1P. That's all. What is this S2P? If you take it as a part of this right angled triangle, then you can understand that this S2P square is equal to this base square, that is d square, plus altitude square. What is the altitude? It is this entire x plus d by 2. Because the distance between two slits is d, half of that will be d by 2. So it is x plus d by 2 square. And then you can say that this is similarly S1P square will be d square plus x in this case, because we are interested in this much of distance, it will be entire x minus d by 2, right? X minus d by 2 square, right? Now if you want to find the difference between these two, so let us individually first evaluate S2p. That will be square root times d square x plus d by 2 square, right? So you will take this d out. You are left with 1 plus x plus d by 2 square by d square, right? And in the next step you can write this is 1 plus, if you use the Bernoulli's theorem, this power will come down. So this is 1 by 2 d square times x plus d by 2 whole square. By same analogy, this factor will be d times 1 minus 1 by 2 d square x plus d by 2 whole square. Then if you do this difference, S2p minus S1p, in short, that is going to be, if you work that out, you are intelligent enough to do that. So if you do this S2p minus S1p, that comes out to be x d by d, right? Now we know that this x d by d can be put to two conditions: the condition of constructive interference and the condition of destructive interference. In this case, we will be equating this expression to the expression for path difference and not phase difference, because we have basically calculated the difference in the path lengths of the two waves coming from two slits. So we will be equating this x d by d either to n lambda or to 2n minus 1 lambda by 2. You are already now well aware of these two conditions. This is the condition that reflects the constructive interference, and this is the condition that reflects the destructive interference. You have already been taught in detail about these things in the previous videos. Today we just need to equate these two with the expression for path difference. Now let us do that. So x d by d is equal to n lambda gives us x is equal to n lambda d by d, right? You can keep on assigning different values to n beginning from 0, 1, 2 to find what is the position of first fringe, second fringe, third fringe, and so on. So let us first find the position of the first bright fringe for n equal to 0, central bright fringe, right? So for n equal to 0, that equal to 0, x equal to 0. For n equal to 1, x1, that is equal to lambda d by d. So x0 is 0, x1 is this much, x2 is 2 lambda d by d. And since you are basically interested in the fringe width, that means you want to see, by fringe width we mean the position of one fringe minus the position of the previous fringe, because fringe width is basically, if you are interested in this width, that will be given by the position of this fringe minus the position of this fringe. So if you do that, twice of this minus this, even if you do it for x3, that is 3 lambda d by d, and you keep on subtracting every previous fringe from the next fringe, yes, that gives the fringe width, and that is lambda d by d. In all cases, 3 minus 2 is 1, 2 minus 1 is 1. So fringe width is, that is denoted by beta, that is lambda d by d. So this is the fringe width in case of constructive interference, that is in case of bright fringes. Now what about the dark fringes? You are again equating this term in case of dark fringes. You are equating this term x d by d with 2n minus 1 lambda by 2, right? So x is 2n minus 1 lambda by 2 d by d. When you keep on giving values n equal to 1, n equal to 2, and finding the value of x1, x2 and x3, and then subtracting the previous from this, again you get the same expression, that is beta is equal to lambda d by d. This means that the width between two bright fringes and between two dark fringes is same, and the expression for fringe width is beta is equal to lambda d by d. Capital D is the distance of the screen from the slits, and d is the distance between two slits, and lambda is the wavelength that you have used to illuminate the two sources S1 and S2. And I think that's all about this Young's double slit experiment.